And actually, for all of the earlier items, most of the time, these FIs are going to be 1. And what we're going to do is, if the weight of this current item is less than or equal to the capacity, set Fi to be equal to 1, else Fi is equal to the fraction that we have left. And what this is going to do is it'll go through this list of items in sorted order by this ratio, the benefit to the weight. So 7 divided by 2, 3.5 in this case, is the best of these ratios in this case. The ratios, if I extend this table by one more row, to look at the DI over WI, that's the cost per pound, if you think of it that way. It's a familiar number. We get 3.5, 1.33, 1.6, and 2.33. And so that's the order that we're going to go through in this greedy algorithm. And what it'll end up doing is assigning 1 to the items with the biggest value, and 0 to all the items with the smallest cost-benefit ratio. And there's going to be 1 item in the middle, probably, that has a fractional value. Sometimes there might even be 0. So if we go through this algorithm, setting the fractional values of each of these items, the first item that we're going to set the fractional value of is item 1, because it has the biggest cost-benefit ratio. And so far we've got a capacity of 10. And this item only has a size of 2, so we can fit all of it, and we set Fi to be 1. Next item is this one with size 6, value 14. We have 8 units of capacity left, and only a size of 6, so we can fit all of this item. The next item has benefit over cost to 1.6. We've got 2 units of capacity left. We used up 2 plus 6, 8. So we have 2 units left. But this item has size 5, so we can't fit all of it. We can only fit a 0.4 fraction of it to fill up those 2 units of capacity. And then these remaining 2 items, we don't have any capacity left, and this formula is going to tell us to use 0 of them. So the optimal fractional solution turns out to be 1 unit of item 1, 0.4 units of item 3, 1 unit of item 6. That's going to give us 21 units of capacity plus 0.4 times 8, which is 3.2, so 24.2. Yeah?
For each item, why are you comparing against W and not the remaining capacity?
For each item, I was comparing against the remaining capacity. So, because that's a mistake.
There's also the ratio.
Okay. More questions about this algorithm? In this case, we ended up with a solution that was what I believe to be the optimal 0-1 solution, including items 1 and 4, and then filling up the rest with a fractional amount of one of the items. In general, that might not be true. The fractional and the 0-1 solutions could be very different from each other. On the other hand, if you need a fast heuristic that'll give you a pretty good solution, it's not a bad idea to try the fractional problem. In many instances, it's not a bad idea to try the fractional problem and then keep the items that you have ones for, throw away the items that you have zeros for, and also throw away that one fractional item. Sometimes that can go very badly though, right? Suppose you have a capacity of 10, and you have some items whose sizes are all 10, the correct solution would be to choose the most valuable of those big items. But the greedy solution would say, if there's some other item with a weight of 1 and a much bigger cost-benefit ratio, take that one item. And so you're leaving a lot of room in your knapsack and possibly getting less value than you might. So the greedy solution solves the problem that it's trying to solve exactly, but it can be very far off from a correct solution to the 0-1 problem. Okay. So now we have the same input, but now we want to make the restriction that we can only include an item or not include an item. We don't get to pick these fractional parts of items. You know, if you're a shipper trying to maximize the value of the cargo that you're shipping in your ship, and you have a set of possible cargoes that you could choose from, you know, some of those cargoes might be things like grain or oil or water that you could take as much or as little of as you want, assuming it's in the proper containers. But some of those other items may be individual units that you can't break up. You know, if you're going to ship somebody a car from Europe to the US, it's not going to be very helpful for them if you ship them half of a car. So the 0-1 knapsack problem, where you're only allowed to choose either to include an item or not include, is also important in a lot of applications. So we're going to solve it with dynamic programming. And so the first thing we need to do is to figure out what the subproblems are. And we want to encode these subproblems by integers as usual so that we can use the encoding as an index into a set. So it turns out the subproblems we want to consider are prefixes of the input set. Plus another piece of information, which is a capacity that might be any number less than or equal to W. Because if we've made some decisions so far and chose some items to be or not be in that input set, that's going to reduce the remaining capacity that we have. And so we need to look at subproblems that have smaller remaining capacity. And this is why the capacity needs to be an integer. So subproblem I, let's call it capital X, is that we want to find the value of the best solution for items 0, 1, up to I minus 1, the first I items, with total weight less than or equal to capital X. And just like in the longest common subsequence, we're going to later backtrack to go from the value of the solution to the actual solution. But in order to set up a dynamic program, we need to use these numbers, the value of the solution, not the set of things that are included in the solution. So that choice is just like in longest common subsequence. And let's call it K of Ix. So we have a recurrence, or we don't have a recurrence yet. We have the thing that we're trying to set up a recurrence for, but we haven't figured out what the recurrence actually is. But that's step one, is figuring out what the subproblems are. Now we need a recurrence. And we're trying to maximize the value. So we want to maximize overall possible choices of the value of that choice. And really, there's only two possible choices. We can include the ith item or not include the ith item. If we include the ith item, if we don't include the ith item, then we're looking at a subproblem where we have one fewer item, because we're not including that one, and the same capacity, because when we don't include an item, it doesn't change how much capacity we have left. Or we can include it, and then we get its benefit, plus k of I minus 1 x minus its weight. So we get the benefit of that item, and that's the BI part of this. But then once we include it, the rest of our knapsack, the space we have left to put other items is smaller. And so we have to solve a problem on these smaller, the smaller set of items still. We figured out what to do with item I, we still have to figure out what to do with the other items, but smaller capacity as well. So all we have to do is take this recurrence and turn it into an algorithm for filling out an array. And you could use it for a recursive algorithm that would be not efficient, because it would basically backtrack through all of the possible ways you could include or not include items. But if we make a dynamic programming algorithm that fills out the recurrence, so we need to allocate an array that runs from an n+1 dimensional array by a w+1 dimensional array, because we need to go from 0 all the way up to n and from 0 all the way up to w. And now for this one, any natural array ordering will work. So for I equals 0, 1, 2, up to n, for j equals 0, 1, 2, up to capital W. It's not as tricky to get the array ordering right in this problem as it is for the longest common subsequence problem. We need a base case. If I is equal to 0, what that means is that there are no items. In our input. We have an input which has 0 items in it. K of ij equals 0. If we have no items, we get no benefit from them. So that's a really simple base case. There's another base case if the weight of item I, if the weight of item I minus 1, the last item, oh, these should be minus 1s here. Minus 1, minus 1. Is item number I minus 1, because we're using zero-based numbering. Little bit of an inconvenience in the way we have to write this stuff, but if the weight of that last item is too big, if the last item doesn't fit, we can't use it. Aij is ki minus 1j. So this one says if we don't have any items, we don't get any benefit. But if we have an item that's too big for the capacity we're looking at in this subproblem, then we might as well just pretend it's not there. It's not helpful. It doesn't actually give us any benefit. Let's see, else we use this max formula. Which looks a little scary because of all these minus ones, but really it's just don't include that last item and get the same value that you had with the previous subproblem. Include that last item, take its benefit, take away its size from the remaining capacity. Let's go through filling out this array using this recurrence for this input. We have capacities going all the way up to 10. And we have numbers of items in our subproblem going up to 5 because there's 5 items in our input. As a base case, when there are 0 items in our input, we get zeros. And what I'm going to do in each step is, for each cell ij, I'm going to take a maximum of 2 previous items. We take the max of cell I minus 1j, and a cell some number of steps earlier. Plus the benefit of that earlier item. So we look up and to our left. How far to our left depends on the size of the weights of these items. What we add to it is the benefit of these items. So item 0 has weight 1. And so in these cases, we're all looking 1 step up or to the left. So base case, when the capacity is 0, nothing fits, 0. Otherwise, we look diagonally and then add the benefit of item 1. Diagonally add the benefit of item 1, or you could copy the number straight up, but that's a 0 and it's not as good. For the cells in this row, we're going to look up or back 2 units. Because the next item has weight 2. So we get a 0 here, a 1 here. Those are both base cases. Because we can't fit a 2-unit item in a capacity of 1. But here, we look back 2 units and add a 7. We look back 2 units and add a 7. We get 8. And then we get 8s all the way down the rest of the row. Got clear?
How do you get the 7?
The 7 is this 0 plus, it's where did I put the recurrence? It's this recurrence, the maximum of the value that's directly above it, a 1, or the value 2 units back plus 7 is 0 plus 7, which is 7. We go 2 units back because the item has weight 2. It takes away 2 units of capacity. We add 7 because that's the benefit of that item. And we do that same calculation in all of the cells of this row. This item, we're going to look 3 units back. So we have base cases, 0, 1, 7. These are all the base cases. Here we're going to look 3 units back, or straight up. And we have a choice of taking 3 units back plus a value of 4. 0 plus 4 is 4, or going straight up and taking the value 8. And actually, in this case, the value 8 is better. 3 units back plus 4, 1 plus 4 is 5, or 8. 8 is still better. 3 units back is a 7 plus 4 gives us 11 versus 8. 11 is now suddenly the right way to go. And now here, finally, we get to take 3 units back, the 8 plus the 4. We can get this nice solution that includes all of these 3 items together and take a value of 12. Row 4, we're looking at benefit 8, but 5 units back. So 5 units back means we can't do it until we get to here. Everything up to here is a base case. 0, 1, 7, 8, 8. These are all the base cases. Finally, we can look 5 units back and take 0 plus 8 versus 11. 11 wins. 1 plus 8 versus 12. 12 wins. 7 plus 8 versus 12 is 15. 15 wins. 8 plus 8 is 16 versus 12. 16 versus 12. 11 plus 8 is 19. So we got a solution for this 4-element subproblem that gives us a total value of 19. But remember, that's not the optimal solution. Now we have a base case that extends even 1 unit further, 1, 7, 8, 8, 11. Now we can look 6 units back plus 14. 0 plus 14 is already better than 12. 1 plus 14 is 15, which is tied with the 15 that we have here. 7 plus 14 is 21, better than 16. 8 plus 14 is 22, better than 16. 8 plus 14 is 22, better than 19. And so this is the value of the overall solution. And to find the actual solution, we can backtrack. This 22 was something that we got as the maximum of 19 and this 8 plus 14. This 8 was something that we calculated as, let's see, it was, We got it from going up here. I think, 888. And then back 2 units. This 1 is something that we got from the 0, and the 0 is a base case. So the horizontal steps here, in this path, the steps that go diagonally rather than straight up, when you backtrack in this way, tell you what to include. You have to include item 0. That's the item with weight 1 and benefit 1. You have to include item 1, the item with weight 2 and benefit 7, and the item with weight 6 and benefit 14. And that's the optimal solution. It's not that problem. Okay, so that's dynamic programming. Lots of different problems can all be solved with the same idea of setting